Okay, let's talk about forces for your GCSE physics revision. I know, it can feel like a huge topic, but you're in the right place. The trick is to get the fundamentals absolutely solid. So in the next few minutes, we're going to nail down those core ideas from the AQA spec, the ones that everything else is built on. Let's jump right in. Right, first things first, we need to tackle a concept that comes up in pretty much every single calculation in this topic: scalar versus vector. It sounds kind of simple, but you'd be amazed how many marks are lost by mixing these two up. So what actually is the difference, and why is it so important you get it right? Let's make it super clear. And here's the deal. This is basically the language of forces. A scalar quantity just has magnitude, which is really just a fancy word for size. So think of things like distance, say 10 meters, or speed, like 20 miles per hour. But a vector has both magnitude and direction. So it's not just 10 meters, it's 10 meters forwards. And here's the crucial bit. Every single force we're going to talk about is a vector. Remember that. So we know forces are vectors. Great. Now, let's see how we can sort them out. It's actually really simple. Every force you'll ever see in your exam belongs to one of just two families. You've got contact forces and non-contact forces. Yep, the names kind of give it all away, don't they? A contact force is exactly what it sounds like. It happens when objects are physically touching. You know, like you pushing a door open or kicking a football. A non-contact force, on the other hand, can act over a distance when the objects are completely separate. Think about a magnet pulling a paperclip towards it. It's literally that straightforward. Okay, so these are the specific examples the AQA spec wants you to have in your back pocket. Now, instead of just trying to memorize this list, just think about that touching rule we just talked about. Is there physical contact? Well, for friction, air resistance, and tension, yeah, absolutely. They need objects to be interacting directly. But what about gravity, magnetism, or static electricity? Nope, they can all work their magic across empty space. That's the key difference to spot in any exam question. Right, let's zoom in on the non-contact force you're going to deal with the most, gravity. And this brings us to probably one of the biggest points of confusion in all of GCSE physics, that classic mix-up between mass and weight. So let's get this sorted once and for all. Okay, if you remember one thing from this whole explainer, please make it this. Weight is a force. It's the pull of gravity on an object. And because it's a force, what's its unit? It has to be the Newton. This is such a classic exam trap, they're just waiting for you to say kilograms, but you know better. Weight is measured in newtons, period. And of course, there's a formula that connects them. You absolutely 100% have to know this one. Weight equals mass times g, which stands for gravitational field strength. Let's break that down. W is your weight in newtons. M is the mass in kilograms, and g is just a number that tells you how strong gravity is in a certain place. Here on Earth, its value is about 9.8 newtons for every single kilogram of stuff. So let's just lay all that out side by side. Look, the main thing to get is the difference between the stuff you're made of and the pull on that stuff. Your mass, the amount of stuff in you, is constant. It's the same here as it would be if you were standing on Mars. But your weight? Well, that's the force of gravity pulling on you, and it would be way lower on Mars because the gravitational pull there is much weaker. One's a scalar, your mass, the other is a vector, your weight. Okay, deep breath. We've covered scalars and vectors, the two families of forces, and that all-important difference between mass and weight. Now for the fun part. Let's put all of that together and see how we can actually use these ideas to figure out the overall force acting on an object. We call this the resultant force. So, what on earth is a resultant force? Don't worry, it sounds way more complicated than it actually is. When you've got a bunch of different forces all pushing and pulling on something, the resultant force is just a single force that represents the combined effect of all the others. Think of it as the net force or the overall winner. And figuring it out, honestly, it's just common sense. The best way to think about it is like a game of tug of war. If you and your friend are both pulling on the same side of the rope, your forces add together, right? You get stronger. But if you're on opposite sides, you have to subtract the weaker person's force from the stronger person's force to see who wins and which way the rope goes. That is all a resultant force is. You're just finding the final outcome of all the pushes and pulls. All right, let's boil all that down. Super fast recap of the absolute essentials. Ready? A scalar has magnitude only. A vector has magnitude and direction. Weight is a force, and it's measured in newtons. And the resultant force is just the single overall force. If you can walk away remembering those 4 points, you are in a fantastic position for your exam. And we'll finish up with a little brain teaser. A resultant force of 0 means an object must be stationary. True or false? Think about a car that's driving along the motorway at a perfectly steady speed. What do you think its resultant force is? This question leads us straight into the next massive topic in physics, Newton's laws. Have a good think about it, and we'll see you in the next explainer.